Hi, everybody. Welcome back to Dave's Math channel. I'm your host, David Tare, and this is my 10th video in my series on algebraic number theory. Today, I'm going to backtrack a little bit. I've been talking about Gaussian primes the last few lectures. We'll get back to Gaussian primes, but before we do, I want to first talk about the fundamental theorem of arithmetic, which I'm sure you guys all learned in grade school. You probably didn't learn the proof, but you probably learned that every positive integer has a unique prime factorization up to ordering of the factors. So that's what we're going to prove today. So anyway, let's begin. Um, we're going to start with a definition of primes. I think you guys all know the definition of prime numbers. A prime is just an integer greater than 1 whose only factors are 1 in themselves. And why are we requiring it to be greater than 1? There's actually some amateur mathematicians who even include 1 as a prime number, but it's not a good idea to let 1 be prime. And the reason it's not, the most basic reason. Remember I was telling you a few lectures ago how fundamental prime numbers are in number theory, and that primes are the building blocks of the integers and even the rational numbers. Well, that's not true if you let 1 be a prime. And in particular, we're not even going to get unique factorization. We're not even going to get unique prime factorization if you let 1 be a prime. Because you can add as many factors of 1 to any factorization of any number you want. For instance, 10 equals 2 times 5. That's a unique factorization of 10 as a product of prime numbers. What if you include 1? Then you could also write 1 times 2 times 5, or you could write 1 squared times 2 times 5. You could write 1 to the 53rd times 2 times 5. So it's no longer unique if you let 1 be a prime factor. That's why we don't let 1 be prime. 1's a special number we call a unit. And I've already been talking about units. Remember I said that the units of the Gaussian integers were plus or minus 1 and plus or minus I. There's 4 units among the Gaussian integers. It actually turns out there's 2 units among the ordinary integers, plus and minus 1. Those are both what are called units. And you can also define primes among all integers, not just positive integers. You just let the negatives of all the ordinary primes also be prime. And this is actually often done. So, for instance, you would say minus 2 is a prime, minus 3, minus 5. The negatives of all the ordinary primes are also prime. You can think of them that way. But they're associates of the... so minus 2 would be an associate of 2. They're essentially the same prime number. We can just add a minus sign, which is really just multiplying by a unit. But anyway, enough of that. So we'll just think about positive integers now, and I hope I've convinced you why we don't want to consider 1 a prime number. But anyway, so in order to prove the fundamental theorem of arithmetic, we need to start with a lemma. And this lemma is actually a pretty famous lemma. It's called Euclid's lemma. And I believe Euclid himself proved this lemma. So here's what the lemma says. Now we're letting P, A, and B be integers, and we're letting P be prime, as a matter of fact. Yeah, they're all positive integers greater than, or A and B don't have to be greater than 1. Well, I guess they do, actually. So we're here, yeah, so we're assuming that, is that right? No, I think A and B are just integers. So here's what the lemma says. If P divides the product of A and B, if P divides A times B, then it has to divide either A or B, or maybe both. That's what Euclid's lemma says. I mean, it seems kind of intuitively obvious, but we still have to prove it. So how do we prove this? Well, if if it divides either one, suppose it divides A, well then we're done because we're just trying to prove that it divides one or the other. So without loss of generality, we can assume that it does not divide A, and now we have to prove that it divides B. So we're assuming it doesn't divide A, and now we're letting D be the GCD of A and P. And that means in particular that D has to divide both A and P. And since it divides P, we know there's only 2 divisors of P, namely 1 and P. But D cannot equal P because we're assuming that D didn't divide A. If D equals P, then D divides A, which means that P divides A, which we're assuming is false. So that means the GCD has to be 1. D has to equal 1. But then by the Euclidean algorithm, we know that the GCD is equal to a linear combination of the things we started with. And in this case, the GCD is 1. So that means there exist integers u and v, such that 1 equals u times a plus v times p. Well, now we can just do a little bit of manipulation. We can multiply both sides by b. So if we multiply the left side by b, we just get b times 1, which is b. And then the right side is just b times the quantity ua plus vp, which is what we had on the right. And now we can use the distributive property. We just say that's equal to uab plus vbp. And now we notice that P divided AB. We assume that P was dividing the product AB. And if that's the case, that means AB has to be a multiple of P. So we can call it K times P, where K is some integer. So now we can replace AB with KP. So now the left side is just, the right side is just UKP plus VBP. Notice that both of these terms have P in them. So we can use a distributive property again. We can pull out a factor of P. We just say B equals P times the quantity, UK plus VB. Well, it's a multiple of P. So we prove that P must divide B, and we're done. That's how we proved Euclid's lemma, which is a very useful lemma. And now we're going to use it. So now we're gonna do the hard part. This is not a simple proof, by the way. There's two parts of the proof. We're now going to prove the fundamental theorem of arithmetic, which says that if n is an integer greater than 1, then it has a unique prime factorization. Specifically, if we write n equals p1, it just has a unique prime factorization. So how do we prove this? Well, first we have to prove existence. So we have to prove that every integer greater than 1 has a prime factorization. We could write it as a product of primes. That's not obvious, but we're going to prove this. So how do we prove it? We're going to prove it by contradiction. So now we're going to assume there is an integer n that we cannot write it as a product of prime factors. And we might as well let n be the smallest such number, smallest such integer. Because if such an integer exists, there has to be a smallest one, right? So if we let n be the smallest one, we're just saying that there's some integer n as the smallest such integer, such that we can't write it as a product of primes. But we know it's composite, because it can't be prime. If it were prime, that would be a contradiction. It would be its own prime factorization, basically. It has just one prime factor, but that's still a prime factorization. So n has to be composite because it's greater than 1 and it's not prime. So that means there have to exist integers a and b such that n equals a times b. But notice that a and b are both greater than 1, because otherwise it wouldn't be a non-trivial factorization. And since they're both greater than 1, that also means they're both less than n. But not that, and since they're both less than n, remember we were assuming that n was the smallest positive integer greater than 1 that didn't have a unique factorization. That means that, or not unique, it doesn't have a prime factorization. That means that a and b, since they're both less than n, they both have to have prime factorizations. So we can write a as the product p1 up to pr, and b is the product q1 up to qs. Well, now what happens if we multiply these two? Remember, n was equal to a times b. Well, we can just multiply all the prime factors. It's just equal to the product p1 times pr times the product q1 up to qs. But that is a prime factorization. So that's a contradiction. So that means that every integer has to have a prime factorization. We didn't prove it's unique, but we proved it existed. That's kind of the easy part. The harder part is uniqueness. But now we're going to prove uniqueness. And again, we argue by contradiction. We assume that there's some number, we call it n again, which has two prime factorizations that are different. And all that really means, we're writing as p1 up to the product p1 up to pr. We're also writing as a product of q1 up to qs. And when we say it's not unique, that means that at least one of the prime factors on either side of this equation is different. there's a pi that's not equal to a qj. That's all that's saying. If we order them, they would be the same. We can first we have to prove one thing. We have to prove that each prime on the left side is different from each prime on the right side. And we're gonna argue by contradiction. So let's first assume that at least one of these prime factors is the same on both sides. Say P1 equals Q1. We can always assume that without loss of generality. If we don't necessarily assume that these prime factors are ordered on both sides, then if they have a common prime factor, we can just say it's P1, which is equal to Q1. Well, now what we do is we construct another integer, we call it n1, and we say n1 is equal to n over p1, which is the same as n over q1 because we're already assuming that p1 equals q1. Well, now look what happens. n1 equals the product p2 up to pr, and it's also equal to product q2 up to qs because we just divided both sides by p. We divided the left side by p1, and we divided the right side by q1, which is the same as p1. But now we've kind of contradicted ourselves because n1 is less than n. Remember, we were assuming n was the smallest integer that didn't have a unique prime factorization. Well, now we just found another one, n1, that doesn't have unique prime factorization. Because if this was unique, then that would mean that the prime factorization of n was unique. So we just contradicted ourselves. Therefore, we're not quite done, but we've shown that if we do have a number that doesn't have unique prime factorization, that means that each prime on each side has to be different. That means that the pi's, each pi on the left, each of the p's, each of the prime pi has to be different from each of the prime qj. So now we have to assume that, and now we let and again we factor out p1 from the left side. Now we know that p1 is not equal to q1, but we can still write n as the product p1 times capital P and the product q1 times capital Q. Well, now we can apply Euclid's lemma. Here's where Euclid's lemma comes into play. So we know that n divides the product q1 times capital Q because it's equal to it. That means that it has to divide either q1 or capital Q. Actually, we're doing p. I'm sorry, we're not doing n. We're doing p1. P1 is a prime number. Yeah, so now we're using Euclid's lemma with little p1, and we know that little p1, since that divides n and n is equal to little q1 times capital Q, we know that little p1 must divide little q1 times capital Q, and that's a product of two integers, so that means it has to divide either little q1 or it has to divide capital Q. Well, it can't divide little q1 because that's not, if it did, it would be equal to it. They're both prime, but we already assumed that little p1 and little q1 are different. So that means it can't divide little q1. That means it has to divide capital Q. But here's where we got a contradiction. If little p1 divides capital Q, and remember, capital Q is less than n, because capital Q is just n divided by little q1. Little q1 is a prime, which we know is greater than 1. That means that little n over little q1 has to be less than little n. That's Q. That's capital Q. So capital Q is less than little n, but p1 divides it. And that means that little p1 is a prime divisor of capital Q. But that contradicts what we already showed, that all the prime divisors on the right side of the equation for little n, those are all the q's, the qi's, the qj's, those are all distinct from all the p's. So that means that each prime factor on the left, in particular p1, cannot be a prime factor of capital 2. So we just cannot contradict. We just arrived at a contradiction. And that does complete our proof of unique factorization. A little bit of a complicated proof, but it's a very useful result, and I think it's important to see a proof of the fundamental theorem of arithmetic. So I just proved it today, and as we'll see, just a little heads up, We're going to also prove that the Gaussian integers is also what's called a unique factorization domain. The prime factorization of Gaussian integers as the product of Gaussian primes is also unique. But we have to kind of be a little more specific about what we mean by unique. Up to ordering, not just ordering, but also up to associates. Remember, you can always replace primes by their associates. So you have to be a little bit careful when you talk about unique factorizations, when you're talking about other unique factorization domains besides the integers. Anyway, that completes my video for tonight. Thank you for watching. Long live math, and I'll see you guys next time. Bye.